This week we'll be talking about instrumentation, and the first topic that we'll talk about is RF coils. So I remember from a previous module, one of the early modules, we talked about how we needed to excite the spins in a sample by using another magnetic field that's perpendicular to the main magnetic field. So that's what the RF coil does. It excites the MRI signal, or it can be used to excite and receive the MRI signal. You could have a situation where you have two coils inside the magnet, one that's used to excite the signal and one that's used to receive the signal. So before I go into the designs of the RF coils, I want to talk about some basic circuit theory. If you've seen this before, you can skip ahead. I'm just going to discuss some basics, DC circuits, and some basic AC circuits. The point being that I'm going to eventually get up to the series RLC resonant circuit. So here I'm showing a symbol for a battery, and these lines are just wires. Okay, this line here is a wire. This symbol is a resistor, R. And the convention here is to show the current flowing from the negative side to the positive side in this direction. Whereas the physical reality is that electrons flow in this direction. I'm not sure why the convention is this way, but that's the way it is. And Ohm's law will tell you how much current, or let's look at the first equation. Ohm's law will tell you the voltage across the resistor based upon the current in the circuit and the resistance value. Or if you know the voltage and the resistance, you can figure out what the current is going to be. So here's a picture of a common resistor and a picture of a common battery. This could be any battery, it could be a car battery or a D-cell battery. So capacitance. What is a capacitor? So it's a device that has two conducting surfaces that are separated by what's called a dielectric, and that allows the capacitor to store energy. So here are some symbols for capacitor. These are pictures of capacitors. These little ones here are usually called chip caps. What I'm not showing here and what I'll talk about later on is an adjustable capacitor. So we can actually, by necessity in our RF coil, and I'll tell you why later, is that we need to adjust the capacitance. The unit of capacitance is the farad. What turns out, the way these are designed is a 1 farad capacitor would be very physically large. So capacitors are usually in the picofarad range, where pico is 10 to the minus 5. Whoops, I didn't write that very well. 10 to the minus 15. So again, as I mentioned before, we're building up to the LCR, or the RLC, resonant circuit, and part of that resonant circuit is an inductor. So what is an inductor? It's really just a loop of wire wrapped around a piece of metal. Okay, like as I'm showing here, the different examples. That's why the symbol for inductance looks like kind of a loop. So you have this loop of wire. Some people will write it like this. Okay, of course the ends here would be straight, but that's just indicating that you have some wire that's looping. And the letter symbol is L. Again, I'm not sure why, but that's just the way it is. Okay, so let's look at some simple AC circuits. So I've taken the simple DC circuit and I've just replaced the DC source with an AC source. So the voltage here is oscillating according to sine 2 pi ft. The voltage is still given by Ohm's law, V equals IR. So, but here, now we have a resistance and an AC source. The current and voltage are now sinusoidal. But when we have just a resistance, we see that the voltage and current are in phase. if we replace the resistance by a capacitance, we have, again, we still have V equals IR, but now R is replaced by this thing called capacitive reactance, which really is just resistance that is dependent on frequency. Okay. And what happens with that is that the current now will lead the voltage by 90 degrees. So you have an out of phase situation. Current and voltage are out of phase. Now if we have an inductor, we still have V equals IR in our circuit, where our R is now our inductive reactance, which is given by 2 pi FL, indicating that inductive reactance is a function of frequency. And for this circuit, the voltage will lead the current by 90 degrees. So again, all this is building up to this circuit here, the series RLC circuit, and also to introduce electrical impedance. So in this circuit, we have another AC source. Again, we have Ohm's law, V equals IR, where R is now replaced by Z. Z is a symbol for impedance, and is given, so the impedance of the circuit here is given by this equation, square root of so on and so on. So this is very important, this idea of impedance, because we really, for the RF coil, we need to get to a situation where we have, remember, we have resonance. If we go back several modules ago, we talked about resonance. So in order to efficiently flip our magnetization vector from the z-axis to the transverse plane, we need the B1 field to be set to resonance. So how do we do that in our coil? Well, in our coil, we have an LC R circuit, and from here I'm just showing L and C because I want to get across what resonance is. So if we have this simple AC circuit with L and C in it, again we just use Ohm's law, I equals V over Z, where the impedance now is just XL minus XC. Okay, so you can see now right away that if XL is equal to XC, this current should go to infinity. Okay, and that's our resonance frequency. Is it the frequency at which XL is equal to XC? And this can be solved here. Here, and I'm showing the resonant frequency, or F naught, is equal to 1 over 2 pi square root of LC. So if you look at this in terms of a frequency response, and I'm just showing this frequency. This can be any frequency. I'm just showing 64 megahertz because, of course, that's a lot more frequency at 1.5 Tesla. So at that, let's say that's our resonance frequency. Then the current, as a function of frequency, would take on this value. Right at resonance, we'd be at infinity. And above it, we would go down. So this is just a frequency response of the LC resonance circuit, where the resonance frequency is 64 megahertz. Okay, now let's look at some RF coils. This is just a picture of one RF coil, just to kind of give you a sense of what a real coil looks like. And I'll talk a little bit more about some real designs later. So for the transmit coil, primary design considerations are, of course, that the resonance frequency of the coil has to match the Lamore frequency. Otherwise, we will not have an efficient transfer of energy from the coil to the spins, and therefore we won't flip the spins as we need to. Of course, the coil has to be physically large enough to accommodate whatever anatomy we're imaging. The field that we generate has to be homogeneous or as uniform as possible in space. And we want to minimize the time needed to tip the spins. Okay, so we want to have an efficient transfer of power from the coil to the spins, and again that's a function of the resonance frequency. So the magnitude of, so remember the flip angle equation here. Gamma B1 tau RF is the time that the RF pulse is on, And the magnitude of B1 is determined by the power delivered from the RF amplifier to the coil, where the power, and again, this is a basic equation from basic circuit theory, is I squared R. But again, now we're in an AC situation, so our R is replaced by the impedance. And the Z here is the square root of R squared effective plus this. This again is just the same thing I showed before, XL minus XC. So this is inductive reactance, 2 pi FL minus 1 over 2 pi FC. Okay. And for the most part, R squared effective is the resistance of the body or the sample that we're imaging. So let's look at the transmit chain. What I'm showing on the left side here is a very simple electronics cabinet that you may find in the electronics room of an imaging center. Okay, so in this cabinet we may have, I don't know, this isn't a universal configuration, but you may have an RF amplifier on the top, and you may have the X, Y, and Z graded amplifiers here, spectrometer computer in this position, and the shim power supply. So the shim power supply supplies power to the shim coils, which are inside the bore. But for this discussion, I just want to focus on what's happening in the transmit chain. So first, the thing that happens when we transmit power, of course, is that we being the operator who are controlling the spectrometer, tell the RF amplifier to send a pulse down the wire that's connected from the amplifier to the wall and then to the coil. So this pulse travels down the transmission line and into the coil. So transmission line has its own impedance. So this, what is typically called the characteristic impedance. So that means that the RF amplifier needs to be, the impedance of the amplifier has to match the impedance of this wire, or the characteristic impedance of this wire. And as well, in addition, the RF coil, the impedance of the RF coil has to match the impedance of this transmission line. Or else, if that is not the case, then the power transmitted from the amplifier to the RF coil won't be transmitted efficiently, and there'll be what is called a reflection. So reflection is power that's reflected back to the RF amplifier if the impedance of the wire and the amplifier do not match, or if the impedance of the coil and the wire do not match. So a little bit about the receive coil. So the receive coil, of course, should provide good SNR. It should have uniform receive response over the volume that we're imaging. So remember, if you want to go back to the principle of reciprocity, that's very important. So for SNR, you have to consider two factors: how sensitive the coil is to the spins, and the noise associated with the coil. So if we go back to topic 3 of module 5, I wrote this signal equation down, and this is just here to remind you, okay, what this is. The signal is depending on the Lamar frequency, the volume of the sample, T2 time, the magnetization in the transverse plane, and the magnetic field in the transverse plane created by the transmit coil. Created by the receive coil. This is the magnetic field that the receive coil is capable of producing in the transverse plane. So again, this is from the principle of reciprocity. The receive coil doesn't actually doesn't create a magnetic field in the transmit plane, in the transverse plane, but it has to be able to create a magnetic field in the transverse plane. Okay, so the noise in the coil is given as a proportionality to, as I'm showing here, where K is Boltzmann's constant. So it's proportional to the temperature of the coil. dF is the bandwidth, so this will be our readout bandwidth, and R effective. So R effective is the resistance in the coil, but it's also the resistance that the coil sees. So the resistance that the received coil sees is resistance from the actual coil circuitry, the resistance of the sample itself, and the resistance of the electronics. So that's what R effective is. And in most spectrometers today, that R effective term is dominated by the resistance of the sample. Okay, so that gets a little bit complicated when talking about resistance of the sample, because I know we're not physically connected to the sample, but there is resistance because of dielectric and some other issues related to electromagnetism. But take it by faith that the electronics in our system are really adding only a small bit of resistance relative to the amount of resistance that is generated by the sample. So, and I've kind of repeated that here. So since the effective resistance is proportional to the resistance of the sample, and the resistance of the sample then, and the resistance of the sample is proportional to the volume of the sample, or the sensitive region, then this volume sensitive here, this V sensitive, gets substituted in for R effective into the equation for SNR. So, okay, so you see this omega to the 7/4 power. All right, that's just, you're going to have to take that on faith for now, because there's a long, tedious derivation as to why that is. Okay, so the SNR associated with a particular received coil is given by this proportionality. So look at this, it kind of makes sense. So as the volume goes down, the SNR goes up. Because remember, we don't like resistance. Okay, resistance in general is bad for SNR. So since the V sensitive should be sensitive, not sensitivity. Since V sensitive is proportional to the resistance of the sample, as that volume of the sample goes down, our resistance goes down and our SNR goes up. Also, as the magnitude of the magnetic field that the received coil can generate in the transverse plane goes up, our SNR goes up. As the temperature of our coil goes down, the SNR goes up. As the bandwidth goes down, our SNR goes up. Okay, as V sensitive goes down, our SNR goes up. So let's look at the receive chain. So I'm showing the same electronics cabinet here, but now I want to look at the chain, or the path that the signal, the signal that we're receiving takes. Oops. So of course we start at the coil, and then we go to this thing called the preamplifier. So the signal that we've received, again, this is a circular RF coil, and I'll show you what that looks like later on. It's called, probably we can assume that's what's called a Birdcage coil. This is our magnet. This is our patient table. So the path that the signal that we're receiving takes is along this wire. It makes it to the preamplifier, because remember, the signal that we're receiving is very small. It's on the order of microvolts. So we need this amplifier here to amplify that signal up until the millivolt range, because the computers in our electronics cabinet, or the analog to digital converter that's sitting in the electronics cabinet, doesn't like signals that are in the microvolt range. They're just too small to detect. So we use this preamplifier to amplify the signal. And then, of course, we have the transmission line, and finally the spectrometer. So the spectrometer is really the brains of the electronics. It's not necessary. It's not the operator console. It's the kind of the box that contains the receiver board, where a lot of digital signal processing occurs on the received signal, where some of the waveforms to generate the RF pulses reside, and the analog digital converter resides here as well. Okay, so let's start to talk about some classic designs of RF coils. One first being the saddle coil. The saddle coil kind of looks like a pair of coils that are wrapped on an invisible cylindrical surface, but they're actually one continuous loop of wire. And as necessary, it produces a B1 in the transverse plane that's perpendicular to B0. I mean, that's a given. We always have to have B1 perpendicular to B0. So here I borrowed this image from Joseph Hornack's website. And you can see, if you look at this carefully, okay, here I'm pointing now to the tuning capacitor. But if you follow this wire, it is one continuous loop of wire, okay, out. And this is the saddle coil, I guess, because it looks maybe a little bit, of course, looks like a saddle. So B0 is along this direction and B1 is perpendicular. Now, unfortunately, I have to kind of rush through these designs. I don't have too much more time here, but I want to at least get through some of the basic designs. But each of these designs is very involved. Anyway, so let's continue. The Birdcage coil is a very, very popular coil because the magnetic field homogeneity inside the coil is excellent. And again, the B1 that it generates is perpendicular. Let's say that B0 is this direction here. Forgive me for this poor drawing. And B1, it would be perpendicular this way. So you can see why it's called a birdcage, of course, because you have these legs, and you have the top portion are called end rings. These symbols here are capacitors, and these rectangular blocks here, these are strips of copper. So it turns out that if the current in the legs is sinusoidal, okay, then the B1 it produces is very uniform, and it actually rotates its direction with angular frequency. And that's what leads the birdcage coil to be what's called a quadrature coil, because it can detect circularly polarized magnetic fields. And if you remember way back from, I think it was module 2 or 3, there was a topic on electromagnetics where I talked a little bit about circular polarization. And if your RF coil has a capability of detecting circularly polarized magnetic fields, which the MRI signal is, it's a circularly polarized magnetic field, then you will have an inherent gain in SNR as compared to a coil that cannot detect those kinds of magnetic fields. You would have an inherent gain of about root 2, theoretically it is root 2, or about 41%. So another very, very popular coil is a surface coil, and this is used for localized imaging, where you need really high SNR. So let's say, for example, you want to image just the brain of a mouse, okay, or just a person's knee joint, maybe, or I'm trying to think of another clinical example. It's much easier to think about the animal examples, because if you think about just the brain of a mouse, it's so small compared to its body. So let's use as an example. You can see that for example, let's choose this little coil here. The brain of a mouse would fit really nicely right into that circle there. Okay. Now, if you had a volume coil, you could also image the brain of the mouse, but you're also going to see, or what you're not going to do is you're not going to fill up the coil completely. Okay, so the brain of the mouse will be inside the coil, but there'll be a lot of space surrounding the brain, just air. Okay, and the more air you have in the coil, or the more empty space you have in the coil, the less the coil is filled up. And that's what's referred to as the filling factor. So as you increase this so-called filling factor, you increase your SNR. So with a surface coil, you have a very high filling factor because you can usually fit most, if not all, of your sample inside the coil, so that your filling factor is very high. So now the phased array. This is a newer design, and so this kind of a coil is used also for high SNR, but if you want high SNR and you want a large volume, so let's say, let's think of a clinical example. Let's say we're going to image a human spine. Okay, we could use a very, very large birdcage coil, but again, we're at the same problem where we have a lot of the coil space is not filled up. So instead, what people have done is they've designed a very large surface coil that is an array of small surface coils that can be laid directly onto the spine. So let's see if I can draw the spine here. Here's the spine, spinal cord. So now, if you lay these surface coils like this on the spine, forgive my art again. Here's the spine. So now what you've done is you've covered most, if not all, of the spinal cord with one effective coil. Although the array coil is several coils, it really acts as only one coil. And this technology is much more complicated than the regular surface coil, as you can see just from this really simple image I'm showing over here, where you have 3 coils, and you can see the circuitry here is a little bit more complicated. We have a BNC cable, of course, going into each of them. So each coil has to be excited, but the coils, what's important, and the reason you see this overlap here, is because if you didn't have overlap, the coils would talk to each other with this metric called mutual inductance, and you don't want to have this mutual inductance. So what they've done is they've overlapped them in order to reduce that mutual inductance, and so they act more independently. And you can see some other circuitry here this is called decoupling. So then kind of gets a little bit beyond how I understand how these work. But again, these are very much more complicated than regular surface coil, and they can be much more complicated than even what I'm showing here. So for example, I think state-of-the-art phased array coils have upwards of 64 or 128 elements. So now if you picture the birdcage coil going over the brain, okay, you can see that, or picture a soccer ball, for example, the soccer ball with the different little octagons. People have made coils like that. In this phased array coil, we have this multiple coils that surround the brain, and this not only helps with SNR, but it can be used in addition for parallel imaging. So if you want to take a scan faster, you can use the signals from each of these coils to fill up K space quicker. And parallel imaging is, again, its own branch of MRI, so I can't really get into it here, but I just want to make you aware of the 2 main functions of the phased array coil. And the last coil I'll talk about is a cryogenic coil, which is really neat. Mostly, I think it's right now only used for animal imaging. But the the point is that the coil itself is cooled down to about 20 degrees Kelvin. So if you remember the noise equation that I wrote down, the noise N is proportional to T coil IL. Okay? So if we I'm sorry, it was 1 over T coil. So if we reduce the temperature of the coil, I think there's a square root in here too. If we reduce the temperature of the coil, we increase. Okay, I just erased that because I think I made a mistake. But anyway, the noise in the coil is a function of the temperature. So if we reduce the temperature of the coil, we reduce the noise. If we reduce the noise, of course, our signal to noise ratio will increase. So what happens in this is the element, which it is inside of this white material. This is actually not the RF, the inductor element, but this is cooled to about 20 degrees Kelvin, and the preamplifier is also cooled down to about 77 degrees Kelvin. These coils are expensive. You do need a large facility, a large amount of resources, such as you have to pump liquid helium into the coil. You have to make sure there's these heat exchangers that you need, a lot of special cabling, special tubing, but they really are nice because you do get an SNR increase of about 2.5 compared to a room temperature coil. So the main applications are right now for MR microscopy in small animals. So if you want to look at, again, brain of mouse is a good example. If you want to look at the brain of a mouse with very high resolution, around 20 micrometers isotropic, so 20 by 20 by 20 micrometers, you can do that with this kind of coil. Also for high resolution NMR spectroscopy. So if you have, I have to stop now. I know this is a longer video than usual. If you have questions, please let me know. I think I have a little bit more to go here about matching, and I hope you guys can go through this. I don't want to spend too much more time, but this is an important topic, because what we're doing before we actually get the, let me kind of reset here. Let's say before you actually use a coil for the first time, what you need to do is you need to tune the coil to the resonance frequency. So we talked about that before when we discussed the resonant frequency in an RLC circuit. We also have to match the impedance of the coil to the impedance of the transmission line. So we do that by designing these capacitive matching networks, where what I'm showing here is a V source, so this would just be our RF amplifier. Z0 is just the impedance of the transmission line. So on the coil, so this L and R, this L represents the RF coil, this R represents the resistance of the electrical, the actual resistance of the coil. Each coil has some DC resistance to it, as well as impedance. What happens on the circuitry that's included in the RF coil is you can have something that I'm showing similar to what I'm showing here, where you have a couple of adjustable capacitors that are used to match the impedance of the coil to the impedance of the transmission line. And this matching condition occurs for this setup when you have Z0 is about equal to 1 over and so on. The tuning condition happens when you have this situation. So you can see the need. Usually L is fixed. So if L is fixed, then in order to tune the coil, you can see that we need to change C1 and C2. So we need to be able to do that manually. Okay, so I'm going to leave you with this slide. This is just something, if you want to look at it, please do. It just gives you an idea of different shapes of different coils for different body parts. And I've also posted another video that shows a design of a surface coil. It's in a digital format, but you'll be able to see the internals of the coil, where this matching network is, where these rods that are used to manually adjust the matching capacitors. Just gives you an idea of what a real coil may look like. Okay, thank you.